Hello, I'm going to discuss my final project, which is an implementation of DiffuserCam. All the cameras that we use in our daily life have lenses. They are expensive, bulky, heavy, and fragile. So the natural question is, must cameras have lenses? Recalling the point spread functions we learned in camera aberrations lecture. The reason we use lenses is that it can focus all the incoming light from a point source to another single point on the camera sensor plane. If without a lens, the sensor will receive almost all white image, which is hard to decode any information from. But with a diffuser and a small aperture, we might just as well encode the signal, and here is the point spread function of the light source on a diffuser. An interesting feature of this PSF is that it is shift invariant when the depth doesn't change, and if you change the depth, it will just scale the PSF, which could also enable us to reconstruct the depth information. Since light transport is linear, let's go through the forward model, the model which turns an image to a sensor result. So here is a PSF of a point source. And for an image, we can just treat it as a linear combination of all these point sources. And thus, it is just a convolution of the image with the PSF. Because of the large kernel size, the edge effects are not negligible. So considerable amount of the image lies outside of the sensor plane. That means we also have an operation that is cropping. So the forward model of the DiffuserCam is just a cropping after convolution, because convolution is just a element-wise multiplication in the Fourier domain, and all of these operations are linear, so we can just write it as a linear operation. And now we would combine all these coefficients as A, and then formulate an optimization problem because the it might not be invertible. We cannot solve this directly by deconvolution because of the cropping, but its gradient is simply A Hermitian times Ax minus Y. We cannot just do the matrix multiplication because all these matrices would have elements that is the squared number of the number of pixels. But as we discussed, we can compute A times something or A Hermitian times something without explicitly formulating the matrix, just like what we did in optical computing. So to compute A Hermitian, we notice that C Hermitian is just zero padding, and the other part, which is all this part, it's another Fourier transform. And now we can set up our experiment. This is the image light source, and this is the sensor. When we are doing the experiment, the light is shut off, so the environment is dark. So for the cameras, we'll build 3 diffuser cams with 2 different types of sensors, and here are their PSFs. We will compare them later. Here we also show the optimization process, which we discussed several slides ago in 200 iterations in this video. Besides, we also implemented a GPU version of this optimization, which can be computed in real time. So here are the results. For camera 1, it looks pretty much like a low frequency version of the original image. For camera 2 and camera 3, it's a bit worse. Why? Because there are actually 2 kinds of sensors. For camera 2 and 3, they are actually using this IMX219 sensors. It's easy to unscrew the lenses off, but its minimum focal distance is a bit larger than the optimal. But in contrast, the other type of sensors, OV5647, it's difficult to tell, but as soon as you tear away the camera mount, it doesn't have a minimum focal distance. But the problem is it's extremely fragile, as shown in this $70 worth of cameras here and the preview of a permanently damaged camera. So due to time constraints, the presentation only have a part of the experiments I've done. If you are interested, please find more details in the report and ask me if there are any questions. Thank you.